Hello everyone, my name is Soha and today I'm presenting question 5 and 6 of homework 5. We used MLR to investigate the relationship of BMI with other predictive variables to address missing data, assess effect modification, address violation of model assumptions, and address potential outliers in the analysis. The variable description include the dependent variable was BMI and the predictive variable were MDS, gender, age, race, education, income, depression, and anxiety score, physical limitations, and frequency of alcohol use. Statistical tools include the MLR was conducted to examine association between BMI and key predictive variables. Statistical tests such as SUEST, Lingam, and interaction tests were used to evaluate the potential effect modification. Model assumptions were checked using histograms, IM test, Bruce-Pagan for heteroscedasticity, and variance inflation factor for multicollinearity. Outliers were assessed through residual analysis and DF beta values. First, we look at the model with newly imputed values after addressing missing data. The number of observations changed from 325 to 379, and R and adjusted R squared values were 0.1762 and 0.1538. MDS female age, ADL, and alcohol consumption, all variables were significant. Now look at the MLR analysis of BMI with ADL and gender interaction. The number of observations remains the same, still 379. R squared and adjusted R squared changes a little bit. Interaction term FMX ADL was significant with a p-value of less than 0.001. MDS female age and alcohol consumptions were still significant. However, ADL changed to non-significant with a p-value of 0.977. The slight changes in beta coefficients were also observed for predictive variables with significant p-values. Then we also performed Lincome test and it shows a significant p-value. This confirms that ADL has a substantial positive effect on BMI, especially for females, so adding the interaction term significantly improves the model. We also performed a likelihood ratio test, which gave a chi-squared statistic of 13.81 and a p-value of 0.0002, indicating that the interaction term significantly improves model fit and should be retained in the model. Then we rescaled MDS and create a binary alcohol use variable to enhance the model. The number of observations remained the same. R squared and adjusted R squared changes a little bit. MDS 1000 and alcohol use both were significant with a p-value less than 0.001 and other covariates remain largely unchanged. We checked linearity assumption for continuous predictive variables. The first plot shows a relatively flat trend between MDS and BMI. The second displays a slight negative trend between age and BMI. The third plot for depression score shows a slight downward trend, and the fourth plot for anxiety score exhibits a mostly flat trend with slight upward movement at higher values. Then we assess the impact of quadratic terms on the BMI prediction. R squared and adjusted R squared were almost the same. We added several quadratic terms in the model to capture potential non-linear relationship between BMI and independent variables. 875 CTR shows a significant negative association with BMI. MDS 1000 CTR remains a significant predictor, and the quadratic term for MDS 1000 SQ is now marginally significant with a p-value of 0.067, suggesting that the curvilinear effect of MDS and BMI is weaker on the reduced model. The mean VIF is 1.58, so there is no multicollinearity in the model. Cameron and Trivedi IM test showed a total p-value of 0.5831, suggesting no sphere heteroscedasticity, skewness, or kurtosis issues. The Bruce-Pagan test was significant, indicating potential heteroscedasticity. The residual histogram suggests a near normal distribution. Then we had an interaction between alcohol use and 875 CTR to further improve the model. Number of observations were still the same. R squared and adjusted R squared were 0.2016 and 0.1799. The overall model is statistically significant with a p-value of less than 0.001. Alcohol use is not significantly associated with BMI. Age-centered 75 years associated with BMI, indicating that the BMI tends to decrease as individuals age. The interaction between alcohol use and age is not statistically significant. The Bruce-Pagan test is significant, however, the IM test shows no strong evidence of heteroscedasticity or non-normality. VIF values indicate no square multicollinearity with all VIF values below 4 and the mean VIF of 1.96. The histogram of residual showed near normal distribution. Then we have a graphical presentation of adjusted regression line. The scatter plot shows the association between BMI and age stratified by alcohol use. Individuals who do not consume alcohol are represented by green, and who do consume alcohol are in blue. Both groups exhibit a negative trend indicating a decline in BMI with increasing age. The regression analysis supports this, with age having a significant negative coefficient, suggesting that for each additional year of age, BMI decreases by approximately 0.25 units on average. The interaction term between alcohol use and age was not statistically significant, meaning that alcohol use doesn't significantly modify the relationship between BMI and age. However, visually, alcohol users appears to have a slightly steeper decline in BMI compared to non-users. In conclusion, we can say that being female was significantly associated with lower BMI, but this effect was modified by ADL limitations where females with ADL had higher BMI. Higher MDS 1000 scores were negatively associated with BMI, but the square term suggests a nonlinear relationship as seen in the quadratic trend in the scatter plots. Age was also a significant predictor, with BMI decreasing as age increased. However, alcohol use did not show a significant main effect on the BMI, nor did its interaction with age, suggesting that alcohol use does not strongly modify the BMI age relationship. The model diagnostic indicates no severe multicollinearity, but heteroscedasticity was detected, which may impact the reliability of standard errors. The model explains about 20.25% of the variance in BMI, indicating that additional factors likely influence BMI. The limitations of the study could include amputation of missing data, which may introduce bias and impact the precision of the study. Thank you.